Hi, this first presentation addressing instruction-level parallelism and its exploitation offers an introductory view focusing on instruction pipelining. Please notice that in this presentation we will be following Patterson and Hennessy's Computer Organization and Design book instead of the other book. After watching this presentation and completing the learning task proposed at the end, you will be able to explain how pipelining can be used to speed up program execution and how it works in practice, taking as an example a simplified MIPS data path architecture. This slide explains the concept of pipelining using a laundry analogy. We have a set of tasks to be carried out and the resources needed to do it. The resources in this case are the laundry basket holding the dirty clothes, the washer, the dryer, and the drawer to store the clean clothes at the end. In a non-pipelined implementation, another laundry process can only take place after the clean clothes are stored in the drawer. This means that each resource will be idle for most of the time. But that is not a good decision, because we might restart to use each resource as soon as each load moved to the next stage. If we do so, each load will still take 4 time slots to finish, but a new load is ready every time slot as shown below, meaning that there has been a 4-fold increase in throughput. If we look at the instruction execution sequence in a standard processor such as the MIPS family, we notice that we again have a sequence of tasks. We have to fetch the instruction from memory, then to decode it while reading the registers, and so on. The resources needed by these tasks are the various blocks in the processor architecture, including the registers, the arithmetic and logic unit, and so on. So, like in the laundry case, we can improve the execution speed by restarting to use each resource as soon as the information moves to the next stage. So let's look at an example. What we see in this table is how long it takes to complete each one of the 5 tasks for various MIPS instructions. Assuming a single execution cycle for each instruction, its duration will be dictated by the instruction that takes longer to execute. In this case, as it is seen on the right, it means that every instruction will take 800 picoseconds to execute because that's the longest time needed. What would be the difference in program execution speed if we use a pipelined architecture that releases each resource as soon as it completes its specific task and made it available to be used by the following instruction? In that case, the clock cycle will be defined by the task taking longer to execute, not by the longest instruction. In this example, this leads to a clock period of 200 picoseconds. A new instruction may be fetched from memory every 200 picoseconds instead of the 800 picoseconds seen for the non-pipelined implementation. In other words, program execution will be 4 times faster. There will, however, be cases when the next instruction cannot start in the following clock cycle, and in such cases we have a pipeline hazard. Hazards come in 3 types, as seen in this slide. If we have a single memory storing instructions and data, for example, then instruction fetch cannot overlap with data access, and this is a structural hazard. It may also happen that one instruction needs to use data that is still in the pipeline, and that would be a data hazard. A typical example is when the result of an addition is needed by the next instruction. And finally, it may also happen that we need to postpone a decision because the result of a given instruction is not yet available. And that is an example of a control hazard. In a conditional branch, for example, we cannot know beforehand if the next instruction is to be fetched from the following memory position or from another location dictated by the branch. We considered 5 pipeline stages in slide number 5, meaning that we will have up to 5 instructions in the pipeline at any given time. Those 5 stages are shown here in the processor data path, and the name of each stage is represented on top, starting with the instruction fetch on the left, followed by the register read and instruction decode, and so on, as shown here. The information flows from left to right, with 2 exceptions, namely the register write back stage to store the result, shown at the bottom, and the selection of the next value of the program counter, shown at the top, which may result from incrementing the current value or from adding a signed offset in the case of a branch. We may think about the pipeline of execution as shown in this slide, which represents what happens in each stage for each clock cycle. In this case, we are looking at the pipeline of execution of the 3 load instructions indicated on the left. This representation seems to suggest that each instruction has its own private data path, but that is not necessary, because we can use registers in between adjacent stages to hold the data corresponding to each instruction as its execution moves down the pipeline. You can see that in this slide where the registers buffering adjacent stages get their name from those stages. For example, the register on the left is called instruction fetch, instruction decode, and it is used to hold the code of the current instruction so that the instruction fetch stage may receive the next instruction from memory. As a final learning task, please read pages 288 to 296, which show in detail the usage of the active portions of the data path while a load instruction goes through the 5 stages of its pipeline of execution. And that's it for now. Thanks for your attention.